Good morning, everyone. Today I will talk about humanoid robots and how to control them in order to reach a kickable position in soccer. So the work I present was done by myself and another PhD student, Quentin Rouxel. So first of all, I will give a little bit of context. So we are working in RoboCup, so in kid-size league. So RoboCup is an annual international robotic competition. That's quite huge because there are around 3,000 people in more than 10 different leagues. And we focus on the soccer kid-size league. So it features bipedal locomotion and custom hardware. So each team has its own robot and its own type of robot. The robot have to embed all the computational power, so you are not allowed to access any other device to run computations. And the robots are moving on artificial turf, which makes bipedal locomotion even harder than it was 5 years ago. So our goal is to approach the ball with a humanoid robot and reach a kickable position. Reaching a kickable position means that the ball is well positioned, aligned with the feet, but also aligned in direction of the goal. So in order to reach this position, we can drive the parameters of the walk engine, so which is mainly holonomic, so you can move forward, you can move laterally, and you can also move in rotations. But still, you cannot change the order suddenly because we are in robotics, so discontinuities in speed is never good. And particularly on bipedal robots, the robot will fall very quickly if you change the order too suddenly. A specific aspect I want to mention is we have heterogeneous robots. So, for example, last year we had one robot which was around 60 centimeters height and another robot which was around 80 centimeters height. So, of course, you have to have similar behaviors but with different parameters for different type of robots. So the main difficulties to approach the ball is, first of all, we are dealing with continuous space for both state and action. We cannot just simply discretize it. And we have also uncertainty on the action results. So, for example, at each step, the robot is slipping slightly on grass. It's hard to model it perfectly, but you cannot ignore it and consider that the robot will act exactly as planned. You also have imperfect motor control, which results in motion of the joints, which are not the one you asked for. And we have discontinuous reward because clearly you reach a kickable position or you're not reaching it. So if you want to minimize the time you spend before reaching the kickable position, well, using a reward function which is continuous and which guides you towards the target will not only be kind of cheating, but it would not allow you to optimize the time you take to reach the kickable position. Then we have a large discrepancy between a theoretical model and reality, because like I said, you have some noise in the control of the motors. It's really imperfect. It has to be because the robot is falling a lot. So if you had perfect motors, the motors will break very quickly. So this large discrepancy has to be accounted for, and sometimes even you have to learn a little bit the modification you have between what you ask and what happens. And as I said previously, you have very limited computational power online. The robot is around 4 kilo and it embeds its own computational power. You are not allowed to have fans, so there's a lot of limitations here for computational power. So the model we use for this problem is a continuous state and action MDP. So first of all, we have 6 state dimensions, 2 for the position of the ball, where we use a polar position for the ball. Then the direction you want to kick to. And finally, the current orders which are used for the work, because as I said previously, you cannot change the orders suddenly, so you need to take this into account in your state space. The action dimensions are the acceleration forward, laterally, and on rotation. So we use acceleration because since we can limit the action, we have a limit on acceleration, so that helps to avoid too much discontinuities on the required speed. So then regarding the rewards, well, if the ball is in a kickable position, that's fine, so we have no cost at all. So. But if we have to do a single step and we are not in a kickable position, then we have a penalty of 1. And if the robot collides with the ball, then we have a penalty of 3. That's a little bit taken out of the hat because it helps the system to converge, but you have to penalize collision, otherwise the robot will go through the ball. And finally, if the ball is too far, then we have a huge cost and we have a terminal state, so it's finished. And for the transition, and we'll speak a little bit more about this after, we have a predictive motion model. So for learning, we have to take into account the difference between what is shared among all the robots, so we can share the same structure for the MDP. We don't need to change the structure from the fundamental structure. But what is specific to each robot is that they don't have the same kicking areas, they don't have the same collision zones, because as you can imagine, the robot which is 80 centimeters 8 will collide the ball sooner than the robot which is 60 centimeters 8. And the predictive motion model can vary not only between different robot types, but between different robots of the same type, because the mechanical use of the mechanical noise is not the same on all the robots of the same type. And for this, we will learn policies on each robot. But I will not, during this talk, I will not go into detail on how we compute this policy, but more focus about the predictive motion model. So we have a basic notion of what we are giving as order to the model. So that's the delta x k and delta y k and stuff like that, and that's what we input to the work engine. But we have some modifications. So here we apply simply linear correction, and we have different types of models we can use. So the first one is proportional, so you see the orange coefficient in the matrix. So it's simply a gain over each of the parameter of the work. Then we have the simple linear, which is with the orange and cyan, where we simply add bias. And then we have the full linear model, in which we also model interaction between the forward orders, for example, and the orientation of the robot, because that's something we observed. If the robot starts to move very quickly and it's a little bit unbalanced to the right, then it starts turning to the right. But if you move slowly, you don't have this problem. So in order to train our model, well, the first thing, of course, is to gather data. So we had a simple procedure. The robot was starting at a given position, known position. Then it worked during 15 seconds using random orders. And finally, we measured the position using a measuring tape, and we approximated the orientation roughly. So that was quite important. That was quite simple, but we tried before with motion capture sets. But the problem is that you cannot take the motion capture set at the Robocop. That's not convenient. So this method is more aiming at having something operational. So we train the model by optimizing the coefficient using a black box optimizer called CMAES, and we seek to minimize the Cartesian and angular errors between what the predictive model announced as result and what we measured. Finally, we validate the model on a set of trajectories we selected, which we did not use for training, in order to get some validation of and make sure we did not overfitted. So here you can see the different models. So of course, if you don't correct, you have always the same kind of error. And you can see that if you use a proportional model, then you quickly have some improvement, even with very few trajectories. But if you use a full linear model, you start by overfitting, and then you have some real improvement with respect to the proportional model. What is interesting also is that the simple linear model seems to always perform worse than the proportional model, which is quite logical because the simple linear model has bias as coefficient, and when we tune up the work engine, we make sure that the robot is not moving when we ask him to stay still. So this bias is very low, so that's more risk of overfitting and not more expressiveness. So the experimental setup we used is we had 3 different policies. The one we used to win the RoboCup last year, CMAES, which is a policy which has the same kind of parameter as the one we used last year, but where the parameter have been optimized using the predictive motion model. And the last one, which is RFPI, is the one we produced using the MDP framework. And we have also 2 different robot types, holonomous robots and almost non-holonomous robots, which are moving really slowly on lateral walk. So we had this problem once, and we wanted to make sure that our setup was able to solve this problem. So in simulation, we had we used random initial states, 50 steps for each trajectory maximum, and 1,000 trials for each modality, because that's simulation, so we can. And well, the average reward, we can see that CMAES always outperforms strongly the policy we had last year, and RFPI even outperform CMAES, so it's better in simulation. But we can see what it gives in the real world. So in the real world, we did not use random position, but prototypical situation. So varying the ball distance, the ball direction, and the kick direction. And well, the ball position was computed according to the embedded vision. So here we see that we have the same kind of ranking, and that's interesting that we have a larger gain for a larger improvement for the almost non-holonomic case. So here you have a small video. I will quickly go to the interesting part. So here we compare the 3 methods with an holonomous robot. So you see the RFPI on the top right, and you can see that the strategies are quite similar. Even if the MDP is a little bit faster, then you have CMAES, and then you see that the one we had last year is much slower. Even with that, we still won. So, well, in here, you have the version with an almost non-holonomous robot. So here you see that the MDP managed to turn before and change its orientation, because it is not able to use properly the lateral motion. But it still failed because the noise model might be inappropriate. So, finally, I will briefly talk about the ongoing project, which is not future work, but ongoing. So we want to also calibrate the noise of the model, because here we use the expert noise we define, and that's not convenient. And we also want to use Markov decision processes to produce higher level policies, such as what kind of kick will we use and to where direction will we kick the ball, because it's not always the best to aim directly at the opponent goal. And well, the RoboCup 2017 is starting in just 1 month, so we'll have the occasion to test the new policies there. And if there is just true idea I would like you to take back home is that calibration of the model can really improve the model. Even if the model is not accurate, you're still improving it, and you don't need to have a large amount of samples. Here we were talking about 20 trajectories measured with measuring tape, and still we managed to improve. So that's like, yeah, it's good to have a lot of data, but even if you don't have a lot of data, you can still make some improvement. And another aspect is the fact that using policy learning with MDP allows to have more adaptability, and I think it's something quite important in robotics because all robots are different, and it helps to save a lot of human time for development. So thank you for listening.
We have time for some questions. Did you think about transferring model knowledge between the robots, or are they just too different?
Sharing some of the model knowledge? Well, actually, that's some of the work we are doing now, is to see, is it really mandatory to test the predictive model on each robot, or can we share some of this information? Because, of course, it helps to save a lot of time when we're at the RoboCup, because calibration of the robot, as we see, even 20 trajectories on the robot, it already takes almost half an hour. So if you have 6 robots, it takes 3 hours. So yeah, that's something quite important. And currently, our results are still that we can use at least some parts. Some of the things are repeatable, but not everything. So.
Anybody else? Do you think it's possible to use past execution logs to extract richer models? So,
excuse me, could you repeat?
Do you think it's possible, or I'm assuming you have execution logs for the matches that you
Yes.
Can you extract data from those logs to enrich your models further?
Actually, yeah, that's interesting. That's something very important for the RoboCup, because there are some situations you can only produce during the games. So you cannot, because you have no opponents when you're training. So yeah, it's something we are trying to do more and more, but mainly for vision. No, currently it's mainly for vision, extracting what the robot has seen during the game. But yeah, I think it should also be interesting, yeah, to have this kind of feature. And moreover, if we have a predictive motion model, we can also see that something is going wrong. And that's something quite important, because we ran the final last year with one of the robots which had a broken motor, and we just noticed that 10 minutes after the beginning of the game. But so yeah.
Thanks.
So the time steps are regularly spaced?
Yeah, the time step, actually we change the order at every step. So the robot is walking, and we have double phase support, where the 2 feet are on the ground, and we change the order at this specific point, because it's important for the stability of the walk engine to avoid changing at any time the orders. So we cannot change while the foot is flying, for example.
Okay, let's thank him again.